Hey everyone, and welcome to my YouTube channel. So here today we are just going to do a simple subtopic which we are going to call Demorgans Rule. So how do you prove Demorgans Rule? So let's say you have this type of a situation. So how do you go about it? So here what you are going to do is first you are going to prove your left hand side, which is this side. You have to take it from the left hand side to the right hand side. So the right hand side is this side. So you want to use this in order for you to come to that. So what are we going to do? So firstly, we are going to have our we are going to let our X be a member of whatever this set is, which is our B union of C complement, like that. If that's the case, if X is a member of B union of C complement, meaning to say everything that is outside of B union of C, then already that means that X must not be a member of your B union of C. It means to say X must not be a member of B union of C. Now already, if you see, this is your B and your C. So B union of C means everything there. So if your X is not a member of B union of C, it simply means to say it must not be a member of X must not also be a member of our B, and X must not also be our member of our C. So depending on your lecture, it's either you just go direct to this step, or you can be able to say others will require you to do this. So remember, union means or. We can be able to say, we can split this by saying that X is not a member of B, or X is not a member of C, like that. So this is the only distinguishing part which I have put in yellow. Some of your lecturers may want you to include this, others may just want you to more like jump to this stage. But the meaning is the same, because already, just as I have explained, B union of C means include everything. Now, if we are saying that X is not an element, or it is not a member, it is not found in B and C, it means to say even the intersection which is your AND is not also there. So this means that X must be a member of B complement. If it is not in B, it means to say it is found outside B. And X must be a member of also C complement. If it is not in C, meaning it's not a member, it means it must be found in C complement. So we can conclude by doing so. Just think of this as you are factorizing. X is common, so we are going to have X as common. Even the element E is common. Then we are going to say B complement, and the meaning of AND means intersection C complement. AND means intersection. So that means that we have established the first part of the equation, which is moving from B union of C complement going to our B complement intersection of C complement. To finish this problem, we are going to say conversely. Let's use blue. So this time what we are going to be doing is getting the right hand side, taking it to the left hand side. So what this means is that we are going to move from B complement intersection of C complement. We want to show that this is equal to the B union of C. So using the right hand side going to the left hand side. So this means that we are going to let our X, be a member of our B complement intersection of C complement. What this simply means is that X already, it is a member, it's showing. So X is a member of B complement, and that's the meaning of intersection. X is a member of our B complement, like that. From the knowledge, we have B and our C here. So if this X is found inside like that, inside B complement like that, it simply means to say if this is our B complement and this is our C complement, it means that our X is found inside C and B. If that's the case, it means that X must not be a member of our B, since the set for B complements X is found there, meaning to say, let's say just B will be outside this set. So that means that already, and we are going to say and already, that means that your X is not found in C. Since this is the set of B complement and C complement, X is a member of that set. It means to say it is not found in a set which could be our C and B could be these sets. So that's the meaning. So X is not, it's just found in B complement and C complement, like that. So if your X is not found in your B, if it is not found in your B and your C, the intersection, which means the middle part, it means to say it is not also found in the B and C entirely, like the whole set, like this whole set. If it is not found in the intersection, it means to say it is also not found in just the B and C. So what we can begin to say is that our X is not a member of our B union of C, since it's not found in the intersection. Now, I have left that line to give room for some of your lecturers. They might want you to change here, so you must study your lecture. So here you will say that so what I am putting in yellow means depends on your lecture. So you will be able to say that your X, here you will say that your X is not a member of B, or your X is not a member of your C, since it's not found inside, it is not found in the intersection. So even the or part, then we got to this. So some of your lecturers may want you to just move from here and move to there. If that's the case, it means that your X is a member of the B union of C when you put the intersection like that. So that means that we have found or verified B complement intersection of C complement will give you it is a subset, or it is contained in B union of C. Then we have the complement. Like, so this is what we have found. So we are just going to be comparing. So you may realize this. So firstly, we began by saying that X is an element of B union of C complement. Now, this wasn't what I was doing when I was teaching for the first time, but look at this. You will realize to say we were just going backwards. So this was our first one that we did, which gave us this. So now for this one, you don't even have to waste time. If you prove one side, just get. So from here, as you can see, this is the step. So yeah, this is the stage. Then we are moving. If you see, from here we began from B union of C going down. But here, it's more like we were just getting this one, which is this. Then moved to this one, which was this. Then we moved to our next stage, which is this one, which is this. Now we have this one, which is the condition. Knowing your lecturer is very important, which was this one. Then we have this one, which was this one. Then this one, which was this one. So all I'm trying to say is that in order for you to prove this one, you just have to know how to prove, let's say, one side. If you know clearly how to prove one side, then for this other side, just go back. Begin from here, go up like that. It's more like you are just copying. Then after that, you can just say, hence, proven. So this is our first type of Demorgans rule. In the next video, we will do the other one.